our last section in Chapter 8 is 8.7 on probability. Now, the first thing we have to understand if we're going to tackle probability is to understand what a sample space is. Now, a sample space is essentially all of the options for whatever our event is. So if letter A is one coin being tossed, the sample space is all the possible options. So heads or tails, that's really it. So the notation, S for sample space, and normally we list all the options in these fancy brackets, heads and tails. That's it. Letter B, if two coins are tossed, so we have to think about all the options. If I flip two coins simultaneously, what are the listed options? So I could have heads, 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 tails, because it matters which coin has the heads and which coin has the tails. Then tails, heads can also be listed, and tails, tails can be listed. And then three coins being tossed. This one takes a little bit of patience to list them all, starting with heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, oops, tails, heads, heads is that one. Tails, head, tails, 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 heads, and tails, tails, tails. So to find the probability of an event, we have to know if our event is E, we have to know the number of ways event E can happen divided by the number of items in the sample space, which is why understanding what a sample space is and how to find it is important because you have to have it for the probability. That is on the bottom is the number in the sample space. And again, the top is the number in the event or how many ways the event itself can happen. So probability is always a number between 0 and 1. And we have to think about what those numbers mean as far as likelihood. So a 0 event would be something that is impossible. It's not going to happen. So something like my head explodes. It's not gonna happen. Moving down to the right, the halfway point is 0.5, or that's where you hear 50-50, so that's equally likely to occur as not. And often we think about something that has a 50-50 chance would be flipping a heads on a coin. So coins are always what I think about when it's 50-50. Moving our way right to 1, that is something that is guaranteed to happen. You could think of a whole bunch of different options. I'm just going to say that something that I guarantee is that the sun is going to set tonight. Okay. So now we're going to actually find the probability of an event. We toss two coins. What is the probability that they both land heads up? So we have to think about, okay, let's go back to our sample space for two coins. That's letter B here. There were 4 total options. And how many of those options had heads, heads? I see one option. So our event is heads, heads. And we know the sample space was 4 options from the front when we listed them all. So since there's only one way that event E can happen, the probability of heads, heads is 1 divided by 4. Now, it doesn't matter to me if you leave your answer as a fraction or a decimal as long as you are consistent and as long as if you do a fraction as long as they're simplified. Some people, it makes a lot more sense to write probability as a decimal or even as a percent, because when you think about it from 0 to 1, and I say something has like a 12/13 chance of happening versus if I say 85% or 90% chance, that you know what that means probably better. So a lot of people prefer decimals or fractions, or I'm sorry, decimals or percents, but if you are a fraction person because they're exact, feel free to use fractions. I will probably be showing mostly fractions because I am a fraction person, but you can always feel free to use your calculator to get the decimal equivalent. A card is drawn from a standard deck of playing cards. What is the probability that it is an ace? So all of these card questions are going to assume that you know what a standard deck of playing cards looks like. If you don't, you can look it up. You can get a deck of cards out, you can look at it, or if we're in class, you can just go ahead and ask me. I'm more than happy to tell you, even if it's a quiz or a test. If you have a question like how many aces are in a deck, I will definitely answer that during a test because it would be difficult for you to do these questions without that knowledge. So, probability that it is an ace. So there are 4 aces in a deck and 52 cards total. So the 52 cards total, that's pretty much like, that's our sample space, are those 52 cards. And then the 4 aces, that would be our event, that there's 4 ways for our event to happen. So the probability of an ace is 4 over 52. And again, I would prefer, if you're going to leave your answer as a fraction, to simplify it. This simplifies to 1/13. Okay, 2 six-sided dice are tossed. What is the probability that a total of 7 is rolled? So notice how we have the first die and second die because order is important. We could have a 1 or a 6, 1 on the first, 6 on the second, and then flip that over, 6, 1. We have a 2, 5, 5, 2, and then 3, 4, 4, 3. So there are 6 combinations for rolling a 7. But how many combinations are there total? How do I know how many events are in my sample space? Well, if I have 6 on the first die, second die, 6 options and 6 options. Remember the law of counting tells us that there are 36 total options if we just multiply the number of each option together. So if I know there are 36 total options and there are 6 ways of rolling a 7, probability of a 7 is 6 over 36, which is 1/6 when we simplify it. Okay, a 12-sided dice can be constructed such that each number from 1 to 6 appears twice on the die. Prove that these dice can be used in any game requiring ordinary 6-sided dice without changing the probabilities of a different outcome. So on an ordinary die, the probability of any number, we'll just do any number, is 1/6, right? Every number happens one time on a die, so the probability of getting a certain number is 1 over 6. On this special 12-sided die, since they said that each number is repeated, the probability of any number is 2 over 12. Again, there are 12 sides, but each number from 1 to 6 is just repeated. So that any number that we picked the first time, this time it's on the dice twice, and there are 12 total options, but it looks like that simplifies to 1/6, so we have shown that the probabilities are the same. In Delaware's lottery game, a player chooses 6 different numbers from 1 to 38. If these 6 numbers match the 6 numbers drawn in any order, so this is important when we figure out how many options there are, by the Lottery Commission, the player wins or shares the top prize. What's the probability of winning the top prize if the player only buys 1 ticket? So the in any order that I circled is important because if we have 38 choices and we choose 6 of them, since we don't care about order, this is a combination. So we have 38 C6 choices for winning. which is 38 factorial over 38 minus 6 factorial, 6 factorial, which is 2,760,681 total combinations of 6 numbers you can get. And if this person only buys one ticket, probability of winning, there's only one event in which this person wins because he only buys one ticket, divided by that huge number. If we want to know as a decimal, so that's an exact value, right? But let's see what the decimal equivalent to that is. Oops, I missed a 2. Okay, I think we got it. Okay, that e to the negative 7 means very unlikely. 0.00000036. That is not likely. So being a statistics teacher and seeing questions like this tell me that you are just not likely to win the lottery. It's just not a fair game. Don't do it. Okay. The number of colleges and universities in various regions of the United States in 2001 are as follows. One institution is selected at random. What's the probability the institution is in one of the 3 southern regions? So these 3 are the southern regions. If I add those 3 numbers up, 1,344, and then total, if I add all of them up, which is going to be my entire sample space, it's 4,178. So the probability of picking a southern institution is 1344 over 4178. Now, a lot of these times these fractions are simplified, but if they're not, like this one is likely not, but let's find out. This is the decimal. If you want to write the decimal down, please go to 4 decimal places and put a squiggly because it's not exactly equal to 0.3217. It's approximately equal to 0.3217, but if I wanted to get the exact simplified fraction, I just do the second answer to fraction, and either of these would be acceptable answers. Okay. Mutually exclusive means that 2 events have no outcomes in common. Meaning, if I take if I have a bowl full of marbles, event A is red marbles, event B is blue marbles, they have nothing in common. If now the probability of a union of 2 events, so another word for the union, you might have heard about the probability of OR. The union is just a more mathematical term for that. So the probability of A or B is given by that notation with the U, A, U, B. We add the probability of A plus the probability of B and subtract off the probability of them occurring together. But if we know that the events are mutually exclusive, then there is no place that those 2 events occur together, which is why it's missing that piece right there. It's not going to have that if we know the events are mutually exclusive ahead of time. So again, mutually exclusive means that the events are not going to happen together. Let's look at this example and see if we have mutually exclusive events. We have cards. What is the probability that the card is either a heart or a face? So the question, if we want to know if they're mutually exclusive, is can you have a heart face? Can they occur together? In this case, yes, you can. There are 3 cards that are hearts and faces. So probability of, let's just do pictures. Heart, whoops. Probability of heart or face. The equation that we just saw up above about the union of 2 events, or the OR, is we do the probability of heart minus the probability of face, plus the probability of face minus the probability of the combination, heart face. So how many hearts are in a deck? So that's going to be, there's 13 in each suit. So this is 13 out of the total 52. And then faces, we have 3 faces per suit. We have the Jack, Queen, and King, and there are 4 suits. So this would be 12 out of 52. And we have to take off that overlap. We have to take off the ones that are repeated here, because we already listed the heart faces here. We listed the heart faces here, and we only want to count them once, which is why we're subtracting off the 3 heart faces. Okay, so I'm going to get 22 over 52. Let's see what that 22 over 52 as a decimal. Whoops, 22 over 52. 0.4231 as a fraction, 11 over 26. Again, either one of those is acceptable. Okay, here it's telling us that we do have a mutually exclusive event that we're going to find the probability of and how that looks a little bit different. So here's a chart of how many employees work for a company and how long they've worked there. So we have 0 to 4 years of service, there were 157 employees who've been there that long, and you can see as the chart goes down the similar categories with how many employees have worked that long. If an employee is chosen at random, what's the probability the employee has worked for 4 or fewer years? So that one is just looking at 4 or fewer. This one's just looking directly at the table. That's the first one, 157. But I actually don't know how many total employees there are, so we need to add up the employees. That is important. 529. So 157 over 529. 157 over 529. Have to know if it simplifies. That's as the decimal. 0.2968, or it is simplified, so this is our answer here. And then 9 or fewer on letter B. So now we have to look at 9 or fewer. This is multiple categories. Here we have the 5 to 9 and we have the 0 to 4. But since you can't have an employee who has worked both 0 to 4 or 5 to 9, there's no overlap. These are mutually exclusive, so I just have to add up the 2 categories for 0 to 4 and 5 to 9 and then divide by the total. So that's 157 and 89 all over 529. Which is 246. As a decimal, 0.4650. As a fraction, 246 over 529. That one didn't simplify either. Okay, so that covers mutual exclusivity. Probability of independent events. So if we're trying to find the probability that A and B will occur, and we know that the events are independent, that means that if I do event A, that's not affecting whether event B occurs. So then to find the probability that they both occur, you just multiply them together. But again, first we have to know whether event A affects event B. If If I have a random number generator, obviously those are independent because whatever the computer picks the first time, as long as repeats or you can have repeats, then they're independent and you can just go ahead and select the second one. From three integers from 1 to 20, what's the probability that all three numbers are less than or equal to 5? So let's find the probability that the first number, just a number, is less than or equal to 5. So there are 5 ways to get that less than or equal to 5, and there are 20 total. So that's 1/4 to get a number less than or equal to 5. I want that 3 times. Probability that we have less than or equal to 5. Since these are independent of each other, we're just going to multiply them together. So 1/4 times 1/4 times 1/4, which is 1/64. In 2001, approximately 65% of the population of the United States was 25 years or older. In a survey, 10 people were chosen at random. What's the probability that all 10 were 25 years or older? So this is certainly independent, okay? So the probability that we select one person in Chicago is not going to affect the person that we choose in Sacramento. You know, if we're doing this randomly throughout the United States, these are certainly independent events. So the probability of at least 25 was 65%, 0.65. So if I want to choose 10 people, instead of doing what we did up above, where we just wrote the event that many times, because here we wanted 3 numbers, so I just wrote it 3 times. I don't want to write this 10 times very badly, but I saw that when you have independent events, you just multiply that probability by itself that many times. So we can take our probability and multiply it by itself 10 times, or the same thing as raising it to the 10th power. And if I do that, I get 0.0135, about 1% chance of having 10 people over the age of 25. Now the complement of an event is just everything that's not in event A. So the example that we just did of greater than or equal to 25, the complement of that would be younger than 25. They're always going to add up to 1. If I know that everything in a sample space is going to add up to 1, and the complement is everything in the sample space that isn't event A, that's how we know that they're going to add up to 1. The notation that we use for the complement is the little hash mark. Call that A prime. And to find the probability of A prime, we do 1 minus the probability of event A. So a manufacturer has determined that a machine averages 1 faulty unit for every 1,000 that it produces. What's the probability that an order of 200 units will have 1 or more faulty units? So I'm thinking about a faulty is 1 out of 1,000. I think the easiest way to do this is the complement of that. So I want to know what the probability of a perfect unit is, and I want to deal with it in terms of the complements. So I have 999 out of 1,000 times I'm going to get a perfect event. So if I know that in my sample space of the 200 units, 1 or more, so we have 0, 1, 2, 3, all the way up to 200. If I'm trying to find this, the probability of 1 or more units are faulty, it's going to be a lot faster for me just to find the probability that there are no faulty units and find the complement. Because 0 and 1 through 200, those are complements. They complete the sample space. So if I just find that 0, it's going to be a lot easier to find than finding 1, then 2, then 3. That would take all day. So I'm going to find the probability of 200 perfect units. And since I already found the probability of 1 perfect unit is 999 over 1,000, I'm going to raise that then to the 200th power. And it's 0.8186. And that's, again, this is the probability of this arrow, 200 perfect units. So now since I want at least one faulty, I'm going to find the complement of the probability I just found, which is 0.1814. All right, that is the last section of chapter 8, 8.7 on probability for pre-calculus.